here, this is a hand-drawn cartoon version of what you see here. These audio spectrographs. And basically, what we have here is a cartoon hand-drawn version of an audio spectrograph, illustrating two separate phonemes, d and do, d and d. I'm sorry, d and duh, right? So this is d and this is duh, and this is the way the spectrograph would look for d and the way the spectrograph would look for duh. Of course, the blue part is the formant transition, and then the red are the formants themselves. So whenever you pronounce d, starts here, and then the vowel sound I is made up of this frequency, this set of frequencies, and this set of frequencies. And then similarly for the do, the D starts here, and then the U part is the formant. And we have these two sets of frequencies here that make up the sound U. What's really interesting about this is, first of all, you would expect to see the I and the U part. In other words, the formants, the red parts, they look different. And of course they are different because I and U are completely different sounds. However, the D part, that is identical. D, I, and D, U are identical, but on the spectrograph, they look completely different. On this spectrograph here, the D sound starts at 2,000, over 2,000 hertz, whereas here, the same exact sound that we perceive as the same exact sound starts much lower at close to 1,000 hertz, which tells us that even though we have these physical sounds that are physically different, we still perceive them as the same way because they are being accompanied by these formants. The other thing too about this weird relationship between the fact that we're able to understand speech from a very wide variety of different physical sounds. Okay, so there's different speakers. If you've ever listened to somebody that has a different accent, or it doesn't matter the accent, the speed, the way words are pronounced. All of these different variations we take into account and are able to understand a really wide variety of different speakers. People are really easily able to do this, to understand different types of speech, no matter what type of weird accents and pitches there are. Machines have a very hard time with this because machines don't have the ability as much as we do to have context around what it is they're understanding. So it's much more difficult for them to predict what it is they're doing. The IBM Watson system does have a speech-to-text system that turns audio sounds into text, and that system relies on a very sophisticated, among other things, very sophisticated semantics to understand what the words are and be able to predict what words are based on the sentences that it thinks the person is trying to say. Here's an example, right? So this is an example of two audio spectrograms. They're both understood to be the same thing. What are you doing and what you doing, right? Notice that, first of all, semantically, the meaning of both of these sentences is identical. However, they sound very different. And not only that, they look very different when you look at them in the audio spectrogram. If you look at these two spectrograms here for the first sentence and the second sentence, you'll notice they're completely different. If you were to design a machine that would understand, say, for example, this spectrogram here, it would completely be unable to understand this spectrogram here. So you see, one of the problems in getting machines to understand spoken words is that they have to deal with this enormous variability in the sound production the way we do. If you've ever had to deal with a voice prompt system on the phone, like if you've ever called a bank or an airline that that takes voice prompts where you say numbers and whatnot, you'll know that a lot of times they make mistakes, and that's because of the very tough problem of not only breaking down these spectrograms, but also breaking down the semantic meaning of the words that the machine is trying to understand. So, um, so we have this ability to categorize a very wide variety of sounds. And we've been able to capture this with what we call voice onset time experiments. And this is the time delay from between when a sound starts and when the voicing actually begins. So, for example, we have two stimuli that are used in these voice onset time experiments: da and ta. Da and ta. Categorizing sounds like da and ta, or any of the other phonemes that you can think of, is a lot like the way we categorize light. Now, if you look at the visible spectrum of light, which on this slide here it goes from 400 nanometers to 700 nanometers, obviously there's millions of different colors in this spectrum. And they change ever so slightly as you go from left to right or right to left. Now, we don't typically look at this and say, I see, millions of colors. We look at this and we say, I see, like, I don't know, 5 or 6 colors, right? I see black, I see red, I see yellow, green, blue, and violet, Those are the only colors that we see. And the sound is very similar to this. The very wide variety of phonemes and sounds that we hear, we categorize into very specific set of buckets where we put those sound things, those sound categories. So here's an example of a spectrograph, a voice spectrograph of the same person saying da and ta. Now notice that whenever I start to say d, and then the onset of the ah part is about 17 milliseconds, and whenever I start to say t, and then the onset of the ah part is about 91 milliseconds. This is the voice onset time. And this is how we tell the difference between da and ta. Our brains perceive da and ta differently because of this onset time, this distinction between this onset time. Da has a much shorter onset time than ta does. What they did in these experiments, in these voice onset time experiments, is they used a computer to create fake stimuli. So they basically went from da to ta, but instead of going from 17 milliseconds for da to 91 milliseconds for ta, they went and they put in a bunch of intermediary voice onset times, say 17, 23, 27, 29, 31, 35, 36, milliseconds, and they increase the voice onset time slowly, and they let people listen to these phonemes with the voice onset time getting longer and longer and longer. And you would think that people would hear maybe a little bit of da and then a lot of nothing. I don't understand, and then all of a sudden, ta, at the very tail end. That's not what happens. What instead happens is, for quite a while, we hear da da da, and then there's this very sudden break where the da goes to ta. And that's called the phonetic boundary, that part where the voice onset time gets long enough for the das to become tas. We refer to that as the phonetic boundary. And here we have this set of data which gives us a really good example of the data from one of these studies. So along the x-axis here, we have voice onset time. So of course we have typical da onset time is about 17 milliseconds, so that's about right here. So we started it really short and increased the voice onset time, and up until about 30-ish milliseconds, people perceived da. Then all of a sudden, 100% of the people heard da. That's what is on the y-axis here. What percentage of the responses were da. But then, once we passed 35 or close to 40 milliseconds, there was a very rapid switch from everybody hearing da to nobody hearing da and everybody hearing ta. And we call this range right here, this break point, the phonetic boundary, the point at which the voice onset time is long enough to convert that da into a ta. And so, yeah, they're going to say, okay, it's the same, and then it starts to sound different, right? And usually it's right around here somewhere. People vary a little bit, but for the most part, it's going to be right around here. And notice this is not a smooth curve. It goes down really quickly. So between about 30 and 50 milliseconds is where there's a little bit of ambiguity, but pretty quickly it becomes pretty obvious, right, when you hit 50 milliseconds that we're not hearing da anymore. We're hearing ta. So there's no such thing as a da and then a something else and then a ta. It's either da or ta. We also uh, uh, use facial feedback when we're perceiving voices. So not only do we listen to the sound of the voice, we also will watch the movement of the lips and the movement of the mouth. This is really obvious when you are, for example, talking to somebody who maybe is speaking a different language than you're used to speaking normally, or perhaps a foreign speaker who is pronouncing things differently. We will tend to focus more on the face, even particularly the movement of the mouth, to try to understand what's being said. This is really well demonstrated in a very famous effect called the McGurk effect. And the best way to show you the McGurk effect is simply to show you this video that describes it really well. Well, thanks to the assholes at YouTube, I cannot include this video directly in my video because it is a copyright violation. So the URL that you see on the screen, it will take you directly to the video demonstrating the McGurk effect, and I will also post this link in the assignment for this chapter.